This video is brought to you by Sir Isaac Newton, bringing you kinematics and calculus since 1687. So welcome everyone from a very windy Wellington. There is a storm at the moment. If you can hear it perhaps in the background, it's pretty intense, so hopefully everyone is keeping safe. So today we get to a pretty important topic of calculus, and it's the topic of kinematics. Kinematics is really the mathematics of how things move over time. So it's part of physics, and in fact if you're a physics student you should be pretty familiar with the kinematic equations. They're originally, it's debatable, but Sir Isaac Newton really codified them properly. Okay, what are they? The three main sort of things that we're worried about in kinematics is displacement, velocity, and acceleration. And I'm going to give you sort of a mnemonic here. We can jump between them by integrating and differentiating. So if we have the displacement, and we're going to get to what exactly displacement is in a second, and we want to find out the velocity at a certain moment in time. So we want to find the velocity at a certain time. The T stands for time. We would want to go down the ladder, so we want to differentiate. If we want to find the acceleration when we're at velocity, we would differentiate again. Okay, so far so good. So these are all functions, and they're all functions of time. That's what the T stands for. But what exactly are velocity, acceleration, and displacement? Well, let's start with velocity. By the way, there are you can keep on differentiating. The next step down is called jounce, if you're really interested, and the one after that is snap. Crackle is the next one, and pop. I don't think these are used very much at all. I don't think I know. I've certainly never used them, but they are there, and they are kind of poking fun at snap, crackle, and pop, the cereal mascots. What is velocity? Well, velocity is the change, so delta, the change in the position given a change in time. Okay, so the way to imagine it, imagine we have a sort of a starting post here, and we have a little car going across the desert. So the car sort of starts here. Again, this is a maths lesson, it's not an art lesson, and it's going across the desert at some speed, some velocity, and it passes the start here at time equals 0. So sometime later, say 3 seconds later, it'll be here. So the average velocity for that time is going to be the change in the position over the change in time. Well, let's say this is 200 meters down the road. So you're going pretty quick. 200 meters down the road. So your average velocity is going to be 200 divided by 3. But that doesn't mean that you're going at that speed the whole time. You could be getting faster and faster, and say here you may have been going, say, 50 meters per second, and here you may have been going 300 meters per second. So notice the units meters per second, so position divided by time. So in that time you've changed your velocity, but the average velocity is going to be that, whatever that is, 67 meters per second. Pretty quick. I mean, that's about 300 k's an hour. So maybe this is like a pretty supercharged car. There's kind of like it's a rocket car. Okay, so far so good. So can velocity be positive and negative? The answer is yes. It can be positive and it can be negative. When it's positive and when it's negative, if it's positive, it just means it's moving in that direction. And if it's negative, it's moving in that direction. So we sort of set a direction, and it's kind of like the x-axis on a graph. We sort of arbitrarily say this direction is positive, this direction is negative. The question comes now, what is the difference between velocity and speed? So most people kind of think, well, there's no difference between velocity and speed, and 99% of the time you'd be right. In general parlance, the way people talk, velocity and speed are interchangeable, but for physics and for kinematics, they're not quite the same thing. So speed is just how far you've gone, how far you travel, divided by how long it took you to get there. Okay. Velocity is slightly different. Velocity is a direction. So if you moved here, from here to here in the 3 seconds, your velocity would be positive. However, if you were moving kind of from here, let's sort of change color. If you were moving from sort of here to here, though, your speed would be kind of, you wouldn't really think that your speed is, you would say your speed is, well, the distance that I've moved in this direction over the time, but you would have a negative velocity, meaning you're going backwards. So this way you're going to have a positive velocity, this way you're going to have a negative velocity. Which way is which? Well, we just arbitrarily decide. We're just going to decide, well, the car's going that way, so we're going to say this way is positive and this way is negative. It's a subtle difference, but it is a really, really important difference in physics, because things can change direction. And even though your speed doesn't change, your velocity can be very different. So that brings us to acceleration. What is acceleration? Well, acceleration is a function of time, so it's acceleration at some time, and this is the change in the velocity over a change in time. So it's how quickly you're speeding up or slowing down. So in your car, if you want to increase your velocity, you hit the accelerator. strangely, when you want to decelerate, you don't hit the decelerator, you hit the brakes. So it's change in your velocity over change in time, and velocity itself is a change in your position over time. So the unit for this is going to be meters per second per second. So your velocity changes by the second. Can acceleration be positive or negative? The answer is yes. If your acceleration is positive, so it's a number greater than 0, it means you're speeding up. If your acceleration is a negative number, so it's a number less than 0, it doesn't mean you're going backwards, it means you're slowing down. All right. We're not going to worry so much about the direction with acceleration. Next year, you'll need to master that. And in physics, you probably need to master that as well. All right. Let's get to the other one up here. And it is displacement. So why am I saying displacement and not distance? Well, displacement is kind of synonymous with distance, but it's not quite the same. And why do we have the S? Well, D is kind of taken. We use D a lot in calculus and in maths, so it's just arbitrarily chosen again. We're going to say it's S. And again, it's a function of time. So your distance, your displacement changes and is different at different times. So what's the difference between distance and displacement? Well, let's get back to our example of the car going across the desert. If you drive in this direction for, say, 300 meters, you stop and you drive the other way for, say, 400 meters, what is the displacement and what is the distance? Well, the distance you've covered is 300 plus 400, so the distance is 700 meters. The displacement, though, is your change from where you started. And your displacement now is actually going to be negative 100 meters. So you can have a negative number for displacement. You can't have a negative distance. I don't think. Maybe in theoretical physics you could have a negative distance, but not for us. Not at IB and NCEA level anyway. So if you asked a physicist, what was your average velocity? Your average velocity would be negative 100 divided by the time it took you to get there. If you asked just some person at random who isn't doing this course, what was your average speed over that time, they would probably say, well, I traveled 700 meters and it took me so far. You'd be talking about the same setup, but very, very different ways of thinking about it. Okay, so if we have time here and we have velocity here, and our velocity changes over time, and we know that to get from velocity to displacement, we integrate and we stop there. So at this time right here, how far have we gone? Well, graphically, it's going to be that area. So it's just kind of bear that in mind. We're going to do some examples. This may seem kind of airy-fairy and theoretical, but it is really, really important that you sort of get your head around these concepts. There's a difference between displacement and distance, speed and velocity, and acceleration, how we sort of look at acceleration. Don't worry about snap, crackle, and pop and jounce. They exist, but you really don't need to worry about them until second year university, really. All right, let's start with a sort of a practical example. So here is the Burj Khalifa in Dubai, and it is pretty impressive, I can tell you that. It is 828 meters high. And I'm going to stick up on the screen a comparison between the Burj Khalifa in Dubai and the Sky Tower in Auckland. And you can see that it is a huge, huge, huge building. All right. Let's say, though, that at the top here of the Burj Khalifa, let's say we installed a diving board, because obviously it sort of comes out like this. Let's say that we had a diving board and you jumped off that diving board into this water down here. Okay, let's ask a question. How long would it take you to hit the water? And the second question we might want to know is, how fast would you be going when you hit the water? Okay, we need to use kinematics to solve that. So let's do it right now. So the first thing we have to do is we have to set up which way is positive and which way is negative. And I'm going to say that down is the positive direction. We could do it the other way around, but I'm going to say that's the positive direction. That's the direction we're going to go when you jump off here. So you're at the top there and you jump off. You're going to be going in that direction, so we might as well make that positive. Okay. Next thing we need to establish, we need to sort of establish how quickly you accelerate. And the physics students there should be saying, I know that gravity accelerates you at 9.8 and a little bit meters per second, which is an acceleration due to time. So we're going to call it 9.81 meters per second. So far, so good. By the way, there is another assumption. We're going to assume that there's no air resistance. That's not going to be true in this case. You're going to get fairly close to terminal velocity, actually. All right. What that means is that every second you're going to be going 9.81 meters per second faster than the second before. So the whole way down, you're going to be getting faster and faster and faster. Okay, so let's look at where we are and where we want to be on our ladder. So here's acceleration, here's velocity, and here's displacement. What have we got and what are we looking for? Well, we want to know how long it's going to take to hit the water. And in fact, for that, we need to work this one out. because that has time in it, and we know the distance is going to be 828 meters. So S of t is going to be 828 meters. We just don't know what t is. We also need to establish what is the initial velocity and what is the initial displacement. Well, the initial velocity when we start, so velocity is 0, we're going to say it's 0. We start from 0, we sort of step off the diving board and just go down. What is our initial displacement when we start, when time equals 0? That's also going to be 0, and this is going to come back later on. These two are going to be important later on. Okay, so where are we? Where do we want to get to? We want to work out how long it's going to take us to get to the bottom, so we need to get there, and we want to work out how fast we're going to be going. So in other words, what's our velocity going to be? So we need to get there as well. Where are we? Well, we start here because we know that our acceleration is 9.81. So we're here, we want to find that, we want to find that. So let's do it. Let's start off with the initial statement. So the acceleration at time is going to be constant, and it's going to be 9.81 meters per second. I'm going to not put the units in for now. Okay, we want to get to velocity, so we need to go up one rung, so we need to integrate. So let's integrate that with respect to time. So velocity with respect to time is when we integrate acceleration with respect to time, if you're wondering what those symbols mean. So let's integrate that. 9.81, when we integrate that, we're going to get 9.81 t, I guess, divided by 1 plus c. Now what's our c? C is going to be our initial velocity, and we know our initial velocity, and it's 0. So therefore the velocity at any time is going to be equal to 9.81 times the time in seconds. Okay, so we've kind of got that. We need to get here though. We want to know how long it's going to take us to go this whole distance down here. What do we need to do? Well, we need to go up a rung, so we're going to integrate again. So displacement is, we take the velocity, we integrate that with respect to time. So let's integrate 9.81 t. When we integrate that, we get 9.81 t stays there. We add 1 and we have to divide by that as well. So what is the c? Well, the c is going to be the initial displacement, and we know that it's 0. So we're going to say that's 0. And now we have a function for displacement, and that's going to be 9.81 divided by 2 b squared. So let's grab our calculator. 9.81 divided by 2, 4.905. T squared. So therefore now we know exactly where we're going to be for any time, presuming that our acceleration is constant, there's no air drag or anything like that. And that's pretty amazing. Okay, now let's look at our question. So we want to know how long it's going to take us. Well, we know that the final displacement at time t is 828 meters. So now we're going to set this equal to 828 and solve for t. So let's do that. Let's divide both sides by 4.905, or you could just go straight on your calculator, I guess. But let's do it now. So they're going to cancel now. So t squared is going to be 828 divided by 4.905. I have no idea what that's going to be. So 168.807. I think if you're falling from the top of the Burj Khalifa, kind of a 1 millimeter is not really gonna, you're not really gonna care about 1 millimeter. So that's t squared. How are we going to find t? Well, we're going to take the square root. And that's going to be to the power of 0.5. So we're going to take the square root. And it's going to be 12.992 seconds, give or take. So you may be asking yourself, well, isn't the square root of that plus minus? Well, you can't really have negative time. I guess you could, but not for us. We don't really care what you were doing before you stepped off the diving board. Okay, we know it's going to take you 12.992 seconds to get from the top of the Burj Khalifa to the bottom. That's a long time to be falling. You pause the video now and you wait for 13 seconds. That's a long time to be falling. How fast are we going to be going when we hit the bottom? Well, we're going to use this formula here now, aren't we? We know what time is. We know what this is going to be. We now need to work out what the velocity at time t is going to be. So we know velocity at time t is going to be 9.81 t, and we know that t is 12.992 seconds. So the velocity after 12.992 seconds is going to be 9.81 times 12.992. And I'm not going to do that in my head, so I'm going to use a calculator. Last answer is already there, times by 9.81. So you're going to be going 127.45 meters per second. Half the speed of sound, almost. Pretty quick. You're going to be going really, really, really fast. And it's not going to be enjoyable when you hit the bottom. Okay, let's do some examples from actual exams so we can get a even better understanding. So I think this is from, I think this is from the 2021 NCEA exam, which is kind of IB SL. Okay, a new car is traveling at 27.78 meters per second, so it's already in the units that we want, and we don't really care that it's 100 kilometers per hour because we want it in meters per second. So I'm going to put a line through that to remind myself to ignore those numbers. it's quite tempting sometimes when you see numbers just to include those numbers. Okay. When the driver sees an obstruction in the road ahead, oh no, the driver applies the brakes. So he applies the decelerator and decelerates at a rate of 2.5 meters per second. So we have our kind of truck here. Maybe it's a tow truck. I don't know. You can tell that I cannot draw to save myself. How long will it take the car to come to a complete stop? Okay, so first thing we have to do, we have to work out which way is positive and which way is negative. Well, in the words of Alice in Wonderland, I'm pointing that way, so I might as well go that way as well. So I'm going to say this direction here is positive. So our velocity that way is going to be positive. Now, our acceleration, we're decelerating. So our acceleration is not equal to 2.5. Our acceleration at any point in time is going to be equal to negative 2.5. Remember, if it's negative, it means we're slowing down. It doesn't mean we're going backwards. It means we're slowing down. And what is this? Well, V0. So when time is 0, we're going 27.78 meters per second. Again, I'm not going to put the units in. It's already in the units that we want. Okay, let's go from acceleration to velocity. So to get from acceleration to velocity, we're there. We want to get to velocity. So we're going to integrate. So let's integrate that. We integrate 0.25 with respect to t, and we get negative 2.5 t. Okay, plus c. What's our c? Our c is what the velocity was when we started. So it's going to be plus 27.78. And are we done? Not quite. What are we looking for? We're looking for how long it takes us to go from that speed there to 0. So we're going to set this equal to 0 and solve for time. So our final velocity, our VF, final velocity, if you're a physics student, is going to be 0. This is our initial velocity, this is our final velocity, and this is our acceleration. Okay, well, let's solve it for time. Let's take 27.78 from both sides. So now it's an algebra question. You could just go do it straight on your calculator. So we're left with negative 2.5 t equals negative 27.78. We're going to divide both sides by negative 2.5. And I want you to sort of keep those, the plus and minuses in the equations, because remember, you can have negative velocity. So just be careful about that. But here you've got a negative number divided by a negative number, so they're going to cancel it anyway. So the time is going to be 27.78 divided by 2.5. So let's put the negative in. 0.78 divided by negative 2.5. 11.112. What? Well, the initial bit of information they gave us was seconds, so we're going to put that unit in. 11.112 seconds, which is quite a long time. That's kind of the time it took you to fall from the top of the Burj Khalifa. That's a pretty long time. Let's kind of take a little detour. If we were to draw this on a graph, So this is time and this is velocity. What's that going to look like? We're going to start here at, what was it, 27.78 meters per second, and we're going to end here where the velocity is 0, and it's going to be a straight line. It's not going to go under that line, and this is going to be at 11.112 seconds. How far have we gone in that time? It's going to be, because we're integrating, it's going to be this area here, which is what we're going to do in this question right here. Okay, using calculus methods, show that the distance the car travels between the time the driver applies the brakes and the car coming to a complete stop is approximately 154 meters. So we want to find the displacement given a time, and we know the time is that. We know we're looking for the displacement. We know the velocity at any time. We already worked that out. So it's going to be, this thing here. And we already know the acceleration given any time, and it's a constant. So we want to work out how far it's going to go and see if it is in fact 154 meters. Let's do that now. And also, because we know that the time is 11.112 seconds. All right. We've got the velocity. Let's start there and go to the displacement. So are we going to integrate or differentiate? We're at velocity. We want to get to the displacement, so we're going to integrate. All right, so the velocity at any time, we know it's going to be negative 2.5 t plus 27.78. We already worked that out up here. So now we want to integrate this. So the displacement at any time is going to be this integrated. So the negative 2.5 stays there, the t stays there, but it grows 1 in the indice, and we have to divide by that. And this 27.78 stays there, and now it gets a t. So what's the initial displacement? Well, the initial displacement, the displacement at time 0 is 0, because when you start, you're at the start. So the distance between the start and the start is nothing. They're in the same place. Think of it like that. All right. We can now put in the numbers. So negative 2.5 over 2 times 11.112 squared plus 27.78 times 11.112, which is time plus nothing. And now we're just going to put that in our calculator. And if you can hear the wind, it is just an absolute gale force out there. So let's say negative, and you have to remember the negative bit, negative 2.5 divided by 2, I don't know what that is off the top of my head, times 11.112 squared is that, plus 27.78 times 11.112 is 154.34 meters. Which, if you're driving a truck, 34 centimeters is pretty close. is kind of not really much to worry about. So 3 significant figures is 154 watt, 154 meters, which is what we've got. So it's accurate to 3 significant figures. All right, well, let's look at another example. So a truck is waiting at a red traffic light. The traffic turns green, the traffic light turns green, and the truck begins to accelerate at 64 meters per second until it reaches a top speed of 25 meters per second. Okay, so this is our acceleration. Our acceleration, by the looks of it, is going to be constant. Use calculus to find the distance the truck traveled until it reached its top speed. Let's move that down. I was looking at how they related the different questions. All right. So what have we got and what are we looking for? We know the acceleration any one time. It's accelerating, so we're increasing our speed, so it's going to be plus 0.64 meters per second. And our final velocity at time t, whatever t is going to be 25 meters per second. What's our initial velocity? Well, our initial velocity at the red light, hopefully you stop at the red light, is going to be 0. So we're trying to find Vt given Va. All right, so on our ladder, we're at acceleration. We want to get to velocity. We don't really care about displacement really. Oh, no, yes, we do actually. We want to find the distance the truck traveled until it reached its top speed, so we want to get there. So we need to get from acceleration to velocity first, so we need to integrate, and then we'll need to integrate again. So our acceleration, when we integrate that, if the acceleration is 0.64, then the velocity is going to be 0.64 t, and our initial velocity is 0, so plus 0. And our displacement given any time is going to be 0.64 t squared divided by 2. And our displacement when we end is, we don't know what it's going to be, but our initial displacement is going to be 0 because we haven't moved at all when we start. Okay, so velocity 0.64 t, and we want to find out how long it's going to take us until that equals 25 meters per second. So we're going to solve for t. So t is going to be 25 divided by 0.64 seconds, which is pretty slow. Accelerating car. Jeremy Clarkson would not be impressed. 25 divided by 0.64. Oh, 40, nearly 40 seconds, 39.06 seconds. Ugh. Youch. All right, fair enough though. How far are we going to get in that time? Well, we're going to take this number and we're going to plow it into this equation. And so it's going to be 0.64 t squared, 39.06 squared divided by 2. Again, we go to our calculator. So 0.64 times 39.06 squared. Whoa, is that divided by 2? So 488 meters. Wow. So half a kilometer to get up to top speed. Ouch. That's well, I guess it's a big truck. But even so, that's not exactly Tesla acceleration, is it? All right, next question. A car travels at 24 meters per second and the driver sees a hazard and takes 0.8 seconds to react. That's quite a long time. During the reaction, the speed is constant. Okay, so for that 0.8 seconds, I guess they mean you're going at 24 meters per second. Okay. How long do the brakes act until the car stops if the brakes decelerate you at a constant deceleration of 3 meters per second? So acceleration with respect to time is 3.0 meters per second, but it's slowing down, so it's going to be negative 3 meters per second. And then it says, how long do the brakes act until the car stops? Okay, well, if we sort of start there at after 0.8 seconds, because it's asking how long do the brakes act until we start. So we don't actually start until 0.8 seconds. So our initial velocity is 24. Okay. And our acceleration is -3. And again, I'm not going to put the units in. And we want to find the final velocity. So our final velocity is going to be 0 because we want to know when we're stopped, our velocity by definition is 0. Okay, so we've got that. We need to find the velocity, so we need to integrate. So if the acceleration is -3, the velocity is going to be -3t plus our initial velocity. What's our initial velocity? Our initial velocity is 24. All right. So now we want to take this equation and find out when the velocity is 0 and solve for t. So let's take 24 from both sides. Again, I'm sort of making sure we go through all of the steps. So t is going to be equal to -24 divided by -3, which is 8. 8 what? 8 seconds. All right. How far does the car travel? So this is B, while braking. So now we're going to take the velocity function and integrate that to find the displacement. So the displacement, the distance that it takes, is going to be this thing integrated, and t now is 8. So -3t, so we're taking it from up here. We add 1, we have to divide by that number as well, plus 24t. And what's our initial displacement? Well, our initial displacement is 0 because the distance that we've traveled from the traffic lights, well, from when we start reacting to when we start reacting is 0. They're in the same place. Okay. And now we're going to put, wherever we have a t, we're going to put in an 8. So the displacement after 8 seconds is going to be -3, 8 squared divided by 2 plus 24 times 8. And it's going to be a number. So -3 times, so 8 squared is 64, is that 192, divided by 2 is that, plus 24 times 8. So it's going to travel 96 meters. All right, what is the total stopping distance, the reaction plus the braking? Well, that's how far we've gone after we hit the brakes. But remember, we were going at 24 meters per second for 0.8 seconds. Okay, so 24 times 0.8 is 19.2 meters. So the total distance is going to be that plus that. So we grab our calculator again. $115.2 meters. Okay, so I'm going to leave it there for kinematics. We may come back a little bit later on. I wanted to crack on because we're pretty close to the exams. So that's all we're going to do for kinematics for the time being.